By the way, does anybody watch these videos? Do you really? Go back and look at them? Pardon? Some, a little, maybe a lot. Yeah, I'm not trying to get nobody, no true confessions here. I just was curious. Is this just for the people that don't come, or is it for the people that come and want to see it again? It's up to you. I'm not trying to. Okay. So anyway, go to this course and labs, and I want to talk through the lab. Okay. So lab 6. What's the trick on lab 6? There is a trick. So you can't do everything that they ask you to do in lab 6 without rewiring the circuit. So let's go down there and I'll show you how to do it. So this one gets you a full boat RL. This is an R and a C, then an R and an L, and then an RL and a C. So basically, these two are pretty easy and pretty straightforward. This one is not. Why is it not? Because you only have 2 leads, okay? You don't get 3 leads, you only have 2. And some scopes have 3. I grant you that there are those that have 3, but you only get 2, okay? So you just came in, I had handed out homework, which we can do later, but I also handed out a lab and an old test. So there's a lab for you and an old test for you. There's an old test, just 5 sheets. There is a lab for you. There's a lab. There's a lab. We're just talking through the lab right now. Okay. There's the homework. Okay, very good. So if you did not get quiz 4 handed in, you hand it in now. If you didn't hand it in, please hand it in now. Okay. So how do you get the phase angle for this one? Okay, you can get the phase angle for the last one because it's the last one from here to here, but the phase angle for here is from here to here, not from here to here. So what you have to do when you get down to this one and you look at the voltage across here and you look at the voltage across here, and they ask you to look at the 2 of them. What you have to do when you're checking the voltage with respect to the input, here's the input voltage. Okay, so you put one scope lead here, okay, and you go through the resistor, and then you go through the inductor, and then you go through the capacitor. And then you put the other scope lead here, and you look at the phase shift of those 2. That's across the capacitor. But what about the inductor? You have to flip them, okay? This is the secret of this lab. And it's really not a secret because you just have to be inventive because we only have 2 scope leads. Some scopes have 3 or 4 scope leads. We only have 2. So what you do is you have to flip the 2. You have to say, okay, now this is the capacitor phase shift. What about the inductor phase shift? All right, what you have to do is you have to go, you have to go here. Continue with this. Here's your resistor. Here's your capacitor. Here's your inductor. And now you've got the inductor. Right? That's it. But when they ask for the phase shift of the inductor, you have to flip the 2 in order to get this one, because now it's this one to ground. Here's your ground, or 0 volts. This is your other lead. So you have to flip them. Okay? That's it. But that is significant, and if you haven't ever had to do that kind of thing in order to get those phase shifts, anyway, does that make sense? And then how you get the phase shift is there's a button, and some of you found that button, and you can hit it, and you're all set. Some of you may have not, but you can read the phase shift right off of the screen. Does that make sense, everybody? If you've seen that, you know where that's at? The button that shows the phase shift, that shows all that information. If you have to look at the waveforms for the phase shift, you're old school. Now that's the way I was always taught. You have to look at the phase shift. Here's one signal, here's another signal, and the phase shift is from here to here. What is that? Well, it's a part of 90 degrees because from here to here is 90 degrees. Well, this would be about 70 out of 90, okay? But that's not very exact. And that's okay, except for the fact that there's a better way. And the better way is to read the phase shift right off of the screen and it tells you, there's a button on there that tells you how to do that. And again, if you get stuck, I can help you, but I don't know where that button, I'm not very good with this scope, but I can tell you that there's a button on there that'll show you all that stuff. And if you don't know where it is, you can ask me or ask somebody that does know where it is, or third alternative is to have that manual. Bring the manual up and ask how to show phase shift and all that kind of stuff, and it'll tell you exactly where to look. Anyway, any questions about lab 6? Sounds like I'm just kind of ducking this whole lab, but I'm not. That's the key. You have to flip the two. All right? That's it. That's all you got to do. But that makes sense and that works. And okay, anybody still have lab quiz 4 out there? Nope, quiz 4 is. If you have quiz 4, please hand it in because we're going to go through it right now. Please hand it in. Okay, if you don't have it out, if you have it, don't come in at the end of class after I've gone through it and say, here's my quiz 4. Please don't do that. Puts me in a very, very difficult spot. Do I give you credit for it or do I not? And I don't want to. That's how it is. Okay, if you got it, please hand it in now. Or so this is problem 341, I think 341. This is, I had a hard time with this problem. Now, it may just be because I'm not thinking very well because I just, run out of gas or whatever, but maybe it's because it is not an easy problem. It's toward the end, and it's not a direct one. It's not one that you would get. It's not just plug and chug. It's what I'm saying. It's not a simple little problem. Okay, so you have to recognize some stuff on this one, and once you do, it's pretty straightforward, but until you do, it's not that easy. Which one was it? 331. Okay, 331. For the picture in for this picture right here. So most of you got it, which I thought was very good. Now, if you got it through ChatGPT, huh? I can't fault you because that's probably what I would have, if I couldn't get it, I probably would have done the same thing. But, this is like a lot of things. You're not going to have ChatGPT. By the way, how many pages of notes can you have? 3 or 4 on the test. I'm not going to critique you how many pages you have. Don't bring a book. Don't bring your notebook. Don't bring a computer thinking you're going to be able to access a computer. And a good calculator. The calculator. If your calculator breaks, I have one. I have one spare. That's it. If 2 of you have no calculator, if you forgot your calculator, forget your pencil, I've got one to lend. How's that? One of each. That's it. So let's look at this problem 331, okay? So here's your circuit. All right, so you got a capacitor, you got a resistor. Now they don't tell you a lot, but they tell you enough. So you've got an 8K resistor, and the current up here is 1 milliamp. They don't tell you the phase angle. They tell you the magnitude, but not the phase angle. Okay, and here is 2 volts, and you assume this is and it's at 100 kilohertz. 100. It's 10K. 10K. All right, so you've got this. You got 10K frequency, 2 volts, 1 milliamp, capacitor, and resistor. That's all you got. Now, what do you know? You know I phasor for the resistor is out this way. So you know 2 volts and 8K, so it's what? 0.25 amp. What else do you know? Milliamp. What else do you know? Capacitor current goes like that. ICE, current leads voltage in a capacitor, ICE. Okay, so current goes up at 90 degrees. Okay, pure capacitive is 90 degrees. So there it is, 90 degrees. Now, you don't know how far it goes, but you do know this. This is 1. That makes sense? Okay, so that's 1, and this is 0.25, 90 degrees. So what is this? Well, 0.25 is equal to what? Cosine minus 1 of theta, which is that right there. What is that? What is theta? Our cosine of 0.25 equals the degrees of theta. What is that? See, you didn't explain it to us. I didn't explain it. I didn't realize this problem was in there. Okay, so cosine minus 1, 0.25 equals 75 degrees. So theta is 75.5 degrees. So if that's 75 degrees, that's pretty high, that's pretty steep. That's pretty steep. So this is pretty long. How long is it? Okay, now you got to ask the question, what is sine of 75 degrees, 75.5 degrees? So sine of 75.5 degrees is equal to 0.968. So if this is 0.25, this is 1, this is 0.968. What? Milliamps. Okay, everybody got that? Now what is that? I. I is equal to V, which is 2 divided by x sub c. And you can forget about the j. Why does that not matter? Because it's pure j, it's not whatever. You can drop the j. In this case, because there's no j plus some real number, you can drop it. Not usually, but in this case you can. So I, or 0.968 divided by, no, it's 2 divided by 0.968 is equal to what? And this is milliamps, is equal to x sub c. 2 divided by 0.968 times 10 to the minus third is x sub c, which is equal to 1 over 2 pi fc. Now we play the game again. We say move the c over here, move the numbers over there. So we move the c to the left. C is equal to 0.968 divided by 2 times 10 to the third times 2 times pi times 10 to the fourth. C is equal to 7.7 nanofarads. Something like that. Any questions, any comments, any thoughts? Not an easy one. Some of you got it, some of you didn't. Anyway, I'm not going to ask you one like that on a test. That one was not one that I would, if you look at my tests, there's pretty straightforward, but that's not one that I'll ask you. But there it is. So I probably won't ask that one again, but on the other hand, I stumble and finally got it, but it took me a while. It took me a long while. Because I forgot how to do it. And I did not pick up on that. And several of you got it. Congratulations. I don't know how you got it, but you got it. I'm happy for you because you did well. So again, these quizzes are not that, you say, I don't know what to say. I'm just saying that was a hard one. Okay, let's look at the test for a few minutes, and I'm going to go back to chapter 6. Because I want you to go through this test. Please, as you practice this test, I would not write on the test. I would write on another piece of paper. okay? And then you can go back and you can practice it 3 or 4 times, because if you make a mistake on the test, on this piece of paper, you've got it there for the next time you go through and study it. What I would do would be to make a bunch of scratch pieces of paper, work the problems on that, and then have your answers, practice it maybe a couple times, have your answers, and then come to class on Tuesday, and we'll work through this test on Tuesday. We'll just go through it, and I would work it as if I were taking the test, okay? I'll just work it. As you can tell, I don't always come in with all the answers. I come in with, you know, what I have, and then I may work through this test. I may not have time to work through this test, but we'll work through it together just like we're taking it, okay? And then you can go practice it again. After that, you can practice it 2 or 3 times, and then you should be ready. Now, I can't guarantee the questions are going to be just like this, but I'll guarantee that they're not going to be, I'm not going to drift far from this, okay? So you'll have 7 or 8 of the questions that will be pretty much identical, except for different numbers. And then you'll have 2 or 3 that'll maybe be a little bit different, but not by much. I'm not gonna go off the rails. I'm not gonna give you a problem like 331. Okay, that's a toughie. Okay, so chapter 6. And I worked, if you weren't here on Tuesday, I worked problem number 29. No, I didn't work 29, or I did not work 29. I'm gonna go back and work problem 29. I worked problem, what did I work? 43, which was 43 was the really messy bad one. I'm gonna work problem 29, which is not as bad. Okay, so that's, and I'd like also to go back and work a couple of problems in chapter 5. We have time, but I want you to get the Kramer stuff. I want you to get how to do that. Okay. Yeah, 43 was when I worked. So did I work number 20? No, I did not. Okay, so let's work number 20 first. So this is chapter 6. And you notice, I don't think I included, did I include chapter 6 in this test? So I don't think I included chapter 6 in this test, but I probably will, just one problem from chapter 6. And basically, it will be writing a mesh equation to standard form. So that's all it will be. It won't be number 20. But I want you to understand number 20, because that is the nodal method. So chapter 6, problem number 20. Okay, so this is a node question. Use nodal analysis to find the current through the 2.7K resistor. So use nodal analysis on this question. So we're going to use nodal analysis. It says use it. Now, what would be the other way of doing this question? Superposition. Okay. It's being superposition would be the other way of solving it, but we're going to use node, and that's because they asked for it. So that's we're going to do that. So here is at node B is where we don't know. So node B is where we don't know. Okay, we don't know the voltage there. And that's what you do, is you take an unknown node and you basically say the current going in is equal to the current going out. In this case, it's probably correct to say the current it's it's 20, and this is in peak. 20 minus VB plus 5 minus VB is equal to the current going out here. So basically, this is coming in from the left, that's called as I1. Current coming in from the right is I2, current going out is I3. And you write that as I1 plus I2 is equal to I3. And you have to write, you don't have to write that, but now you have to write it in terms of V over R. Okay, so what is the current coming in from the left? It's 20 minus VB over 3.9K. Everybody see that? Current coming in from the left is that current right there. Plus the current coming in from the right is 5 minus VB. So it's the current coming around this way, from here going around flowing that way. 5 minus VB divided by what? The resistance in between. It's 1.8K minus J1K is equal to VB divided by 2.7K plus J4K. Now, what's wrong with this? You got these massive denominators, and that's the problem with this approach. But that being said, you can't do this. So get your calculator out, and you've got to get the VBs on the left, and you've got to get everything else on the right. That's the goal. So the 20 divided by 3.9K has got to go on the right-hand side. So basically, it's going to be 20 divided by 3.9 is equal to 5.128 with a what? Well, let's just solve this. This is 5.128 milliamps, or I should just say 5.128 times 10 to the minus third, minus VB over 3.9K plus 5 over, what is this? This is not 5 over 1.8K. This is a nasty one. So this is basically, you have to find the denominator. 5 divided by what? Parenthesis 1800 minus 1000 I. Parenthesis equals option 1. What is that equal to? So instead of 5 over 1, it's 5 divided by this is equal to what? 0.002428 at angle 29.05. So that is this part. And then it is minus VB over this. What is 1 divided by 1.8? Okay, so what is 1 divided by, or 1 divided by 10, parenthesis 1800 minus 1000 I, parenthesis, is equal to what? 0.000486. So it's minus VB times 0.0004856 at angle 29.05. So we've got this going to the right, this staying on the left, this going to the right, and then equal VB over this. So this is a mess. These are all messy. I kid you not. You're going to hate these, and that's why we really don't ever do them. It's 20 divided by this is this, minus VB over this is this. 5 divided by this is this, minus VB divided by this is equal to VB over 2.7K. What is that? 1 divided by 2700 is equal to 1 over 2700, or 0.003703. So it's VB times 0.0003703 plus VB over that complex number, 1 divided by parenthesis 2700 plus 4000 I in parenthesis equal, Ted. 1 divided by 2700 plus, and you got to put parentheses in there too. 1 divided by parenthesis 2700 plus 4000 I in parenthesis equals option 1, and that is, answer is VB times 0.00022 VB times 0.000200712, an angle minus 55.98. Okay. Out of all that, I get the answer, VB is equal to 4.038 at angle minus 26.019. But that's how you do it. It's a mess. Okay. And then you divide, to get the current through the 2.7K, you divide that voltage by 2.7K plus J4K, and you get the current. And that's how you do it. It's not easy. That's it. What a mess. And they're all little bitty numbers. Okay, let's go backwards to number 19. Now, it doesn't matter whether or not I use, okay, it does not really matter whether or not I use number 19, okay, so 6.19. It doesn't matter whether I go in like this or I go in like this. It doesn't matter. In this example, in the last example, I did this. In this example, I'm going to do this. It doesn't matter because the same answer will pop out because the currents may be backwards. So be it. That doesn't matter. So basically, this point, I'm going to write it as this one right here. So here in number 19, it's 1 minus VB over 75, which is that resistance, is equal to VB over 82 minus J 79.5, which is which is the x of that, okay, plus VB. By the way, I will not give it to you like this. I'll give it to you like this. In a test, if you miss that, the rest of it is messed up, Royal. So I'll give you that much. That's a given. I'm not going to mess around with you having to do this step to get to here. I'll give it to you like this. Sometimes he does, sometimes he doesn't. But in a test, in the heat of the moment, if you miss this, the rest of it, you're had. Okay? Plus VB minus 2 over what? Minus J 31.8. Now this is a little bit easier, but it's still not easy. Okay? So now you get the VBs on the one side. And you can do this a little easier, this one, VB times 1 over 82 point whatever minus J 79.5 plus 1 over a minus J 31.8 plus 1 over 75, which you can kind of use the calculator and get. You can kind of get that. Is equal to 1 over 75 plus 2 over minus J 31.8. And then you can get this. VB times 0.0423 at angle 62.407 is equal to 0.0642 at angle 78.3. Now you're almost there. VB in this case is equal to 1.517 at angle 15.623. And you're done. Except for the fact now you have to, now that you've cracked the code, now you crack the problem. Now you got to go back and look and say, what did he ask for? Did he ask for current, whatever? You found the unknown. You found the thing that you had to crack before you could do anything else. Now that you've got that far, how do you go the rest of the way? No big deal. But you cracked the problem. I consider that 90% done, even though you might not get the final answer. You're 90% of the way there. So, now, why do they make you do all this stuff, right? Good question. It's because they're hard and they take time, but yet it seems like if you can do this kind of stuff, you can do about anything. By the way, the first problem that I had when I got out of school wasn't anything like anything I'd ever studied before in my life. It was I was asked to be an understudy for two other guys who had written a program to track glass on a conveyor system. And lo and behold, the one guy got mad and quit. The guy that really knew what was going on, he was the main guy. He was the confident guy. He was the older guy. But he got mad and quit. Just said, I can't deal with this. They're imbeciles or whatever. He was wrong. He was dead wrong. The people that he was arguing with were right, but he got mad and quit. And the other guy that I was working with, he was called into not being able to go to the plant to actually help start the system up because the plant that he worked at was a union plant, and this was supposed to be a non-union plant, and they did not want the non-union people to succeed. So they did not let him go. So I was stuck by myself as an understudy on a massive project to try to write the code for tracking of glass on a conveyor system. And I had never done anything like that before in my life. Never nobody had prepared me for this. And yet somebody had to do it because that was what they designed the system around, automating so that they knew where every piece of glass was on the whole conveyor system. And one of the first things I did, and I don't want to belabor this too long, but one of the first things I did was I looked at they had a light in that era that showed how much that there were four levels there were four programs that could run, or four level programs. One interrupts. One would be the highest level, which only the system stuff did. Then level one, level zero is the highest. Level two is the next highest. My program was on level 1 because it was the one that had to run for the machine to work. Level 2 was the what they call the booking, or the recording of the data after the fact. Level 3 was the HMI, or the screens, putting a screen up on which is the lowest level. So anyway, I was writing on level 1, and I looked at the screen, or I looked at the light for the one that they already had running. And these two guys had written this, and it was all, they had done one, but it was only for 7 sections of conveyor. And I was writing for 66 sections of conveyor. Same kind of thing, except instead of tracking for one little diversion, I had all these diversion lanes and all that kind of stuff. And so I grappled with that. I said, that light is on very intensely for 7 sections of conveyor, and they used interrupts. So I was tasked with the idea of, nobody asked me to do this. I just thought about it myself. I said, that light is on awful bright for 7 sections of conveyor, a lot of interrupts going on. So I thought, how can I not have to do that? So I thought, well, I'm going to, instead of having it on an interrupt basis, I'm going to have one interrupt, and every 8 milliseconds on a clock, look at the status of these pulse codes, pulsars. And it would be faster than the pulse could go off to on or on to off. So I would catch every one of them. But I might not catch them right on the leading edge. Who cares? As long as I was pretty accurate. So I went ahead and wrote the program based on a scan of every 8 milliseconds on a clock, reading all these 66 pulses. And I had it in my head, and I had it written down, and I had written the code for it, but I hadn't gone to the plant yet and actually tried it out. But in the process of all this, we were going to the plant in May, started up in June. In about February, around the water cooler, my boss, who was not a programmer, said something to somebody else. Oh, well, John did all that with interrupts. John was the guy that quit. And I said, oh, I changed that. I made it a scanned program. For the first time, I thought, Ted, you just got fired. But, he came to my office after that. He's an older guy. He came to my office and said, now, how did you change that? I said, I changed it from an interrupt-driven program to a scanned program because I didn't think I could make it around in time for all those 66 interrupts to actually be to be taken care of without running out of computer time. And he kind of looked at me and he said, can you flowchart that? I hated to do that, but I did it. Took me about 2 days to do that. Took me about three days to explain that to him, how to do it, and all that kind of stuff. At the end of those 2 or 3 days, he said, I think it'll work. Go ahead. It worked. The light on the machine down in Laurinburg, North Carolina, was not nearly as bright as the one that was on at Rossford that only had 7 interrupts. What's my point? You don't know what you're going to get hit with. You can walk out of here and you can be asked to do something, and somebody can quit and somebody else can get diverted or whatever. You can be staring out some of the most difficult problems there is. And I was just an understudy. I was just the third guy in. And all of a sudden the other 2 guys got shot. I was the only man standing. Now the other side of the coin was I didn't get the system started up on June, and they had to run in manual for a couple of months. One day in August, I came in, and I still haven't got this thing started up. And they're still running in manual with a person at the corners sitting there trying to, if they had 2 pieces of glass, one going left, one going right, they would flip the manual switch sitting there. So they have to have everything done in manual by eye instead of having it automated. You can see this. Somebody standing there doing this all day. Don't like that. It'd get messed up and all that kind of stuff. Anyway, so in August, I was walking in, and I've been working at this, trying to get this stuff to be proven without having time. They wouldn't let you because they had to run a machine. This is a big, massive conveyor system in a big factory, all that kind of stuff. They had to keep production up. How are you ever going to get it running if you can't have trial time? How do you do that? I walked in. heard the crushers going. This is glass being crushed. I said, what is going on? Somebody forgot the soda ash. Somebody forgot to order the soda ash. And it's like, duh, dummy. What is soda ash? I had no idea what soda ash was. I said, how many days before they're going to get it? 2. So those 2 days, I took the crushers upstream, lifted them up, put the crushers down downstream from after my program, that I could try my program and see if I could get it. If I get this tracking to work, I was in. And in those 2 days, I was golden. I had everything done and proven. You'd have thought, well, we could just turn on the machine, right? I told the guy, I said, we can turn the machine on. Now the big surprise came. Well, I can't put, okay, this is an automated system. Somebody came down and said that you're going to get these automated sheets and you're going to do everything by optimization. In other words, you're going to optimize everything and it's going to be given to you with a sheet and you just go down and set it up and that's the way it is. The guy said, the foreman said, I can't do that. My boxes are over there and they're not over here. And that cutter head you have on the machine that says that you're supposed to use a cutter head, it's just broken. So instead of 6 screens, HMI screens, all of a sudden I got this sinking feeling like, Ted, every one of those options that you have on that sheet are going to have to be overridden manually. So instead of 6 screens, I ended up with 66 screens. You get the picture? It was one of the biggest messes, surprises in my life. And I got it to work. And there was nobody else. Nobody came and helped me. Nobody came in on their white horse and rode in and said, whatever. Now it had an effect on me because this was 7 months. I finally got the thing up and fully operational end of October. It was everything was up and running. People from Rossford went down there, they looked at that machine and they'd never seen anything like it, like this. By the way, by doing the scanned program, the interrupt was every 1.5 inches. By the scan program, I interrupted it, or I incremented the count every 3/4 of an inch. I went every plus and every minus. I incremented by 1. I was twice as accurate. I was accurate to 0.75 inch instead of 1.5 inch. Every section ran. It ran less interrupt. There was only one interrupt, one 8 millisecond interrupt. But this whole thing with this HMI screen thing, just like, you got to be kidding me. Every section, you have to be able to manually override every part and be able to change anything in this recipe of where they go and how they go and which cutter head and all that kind of stuff. Everything had to be changeable. Everything had to be modified at the site. Okay. So don't feel like this program, this little program here is just, it's not setting you up for failure. It's setting you up so that what? When you hit something that you have no idea what's going to happen, you don't give up. You keep on going. So I'm not saying that you'll ever have a problem like that. And I hope that you don't. I hope you have a good life. It was a mess. 7 months. 12 hours a day, thinking every day you're going to get fired. Came out of it. Okay. There is a correlate. There's a backside to that story. I quit. I had enough. I couldn't. It's not that I couldn't take it, but they didn't help me. Nobody came in and helped me. Nobody came in and did anything. It was just, they were just threw me to the wolves. So I kind of resented it. Kind of was a light word. So again, I came back, started doing some other stuff. And I looked at about a couple of other job opportunities that are out there, and nothing panned out. So I was just okay. Somebody called me about a year after that, and they offered me a job, and I took it. Probably should have never done it, but I did, because I got laid off from that job. The only job I ever got laid off from was that job, but it was because it was a government contract. They promised me it wasn't a government contract, but it turned out to be a government contract. Therefore, when they lost the government contract, they laid off some of the people, and I was the last guy in, so I was the first guy fired. So anyway, that was that. Learned a lot, but I didn't like, but it's okay. Anyway, I got laid off. I have been laid off, okay? So I've done that. I've been kicked out of a plant. I've been escorted out of a plant, not because of something I did, but I've been escorted out. I've done that. I mean, whatever. That was after I became a teacher too, so that was kind of interesting. But so the backside of that thing was after I left, they decided to build another line, and they had other people to do it. And the problem with that other line was that they said anything goes. So now they've got all this flexibility, they build all this stuff in. Anything goes. In other words, I can be at the end of this line making decisions that can affect the overall production of that line. So I can go out here and type something in, and I can call up all kinds of pieces of glass. Wrong idea. What actually happened was, by doing that anything goes approach, they made it so that somebody, a clown down here at the end of the line, can make a decision that can affect the overall production of that line. In other words, they can overcall pieces of glass for the output of a certain area. They didn't take into effect that I can only offload so many pieces of glass on this segment of that line in a certain amount of time. Now, in New York City, what happens if you have the ambassador from Russia comes in, you get gridlock. And that's what that line had, it got gridlocked. Okay? You can just see piece of glass backing up, and what happens when piece of glass back up? Pressure comes down, you lose production. They were losing to the tune of $7 million a year on that line. They weren't making any money, and that almost bankrupted the company. That's what happened to that company. One of the reasons that company is no longer on the New York Stock Exchange was because that decision. And I wasn't there. I've been haunted by it for years because that's why I'm an industrial engineer at my PhD level, not an electrical engineer, because you have to be able to make industrial wise decisions, not just do what they say. You have to think in terms of how is this going to make the company money? In other words, is this going to make is this throughput going to be better, or is this throughput going to be worse? That was a hard one to see for them, and they made a very bad decision by saying anything goes. And that's what was led to by the fact that the first line had that effect. Anything goes. Anything can be done. You can make anywhere, you can call up any piece anywhere, and it'll work. But that led to other problems. And the other problems were, and a clown at the end of the line can bankrupt your company. They can call up something that doesn't work. And you didn't stop them. You didn't say, you can't make more pieces for this part of the line than you can pick up in a unit of time. Because you'll bankrupt the company. And they did. Anyway, a diversion. So now you're all scared you're going to take another job. You're going to walk out today and say, anything but electrical engineering technology. Oh my. No, you're not. Because you've got the idea in mind that it ain't all going to be exactly like this, but it's going to be something. It's going to be something that's probably going to be very interesting. Okay, that's number 19. What else did I want to do? I did number 43 for you already. I wanted to do 27. I think I've got number 7 in. It's in my mind. If I can find it in my book. If I could only find it in my book, right? We do have some interesting stuff second half of this course, and I know that you're getting tired, and I can see it, and yeah, I understand. Well, I can't find it right off. There's 6, 20, 19, 20, 43, 43, and 60. I thought I had 27 someplace. I'll walk out of here and I'll say, there it is, and Just a second, we'll get it, or not. Okay, there's chapter 6, problem 29. Is that what I said? 6, problem 29, yeah. Good on 29. This I assigned as a quiz question once, and I'm, so 653. Okay, so do mesh equations on this 653. So that's what we're supposed to do. So this would be problem number 29, 629. Do a mesh equation for this guy, 20. And then I go up here, and then come down here, over here, and then over here. Okay, so this is my, you do this, and do this, okay? I1, I2. 20, 3.9, J4K, 2.7, K, 1.8, K, minus J1K, 5 volts. Plus on top, both of them. Plus on top, both of them. Okay, now, how do you write this? Start in the left-hand corner. Write the I1 loop first, minus 20, plus I1, I'll use caps because it's easier, 3.9K, plus I1 minus I2, parenthesis, what? 2.7K plus J4K equals 0. Any questions about that? Two, I2 minus I1 parenthesis times what? 2.7K plus J4K plus I2 times 1.8K minus J1K plus 5 equals 0. Sort and sift the I1s, the I2s, the I1s, the I2s, equals something, equals something. Okay, what does that equal? So I got it all in polar. It's all in polar. Okay, this is a very, okay, so you sort and sift, and I got the answers in polar. 7717.51 at angle 31.21 plus I2 times 4828.97 at angle minus 124.01 is equal to 20. See how this goes? It's, you can sort and sift and you get down to this point. This is called standard form, okay? And this is 4825 at angle 0.97 at angle minus 124 plus the I2 5408.32 at angle 53.29 is equal to minus 5. From that, you get I1 is equal to, it's 20 and minus 5, and then this and this over my standard. Okay, so it's this. So here I put my 48.28 and my 5408, I put that, and then I put this whole thing in the denominator, and that's my I1. And it's this times this minus this times this times this minus this times this. And I get, finally, I1 is equal to 2.785 milliamps at angle 3.98. Okay, any questions about that one? Those aren't easy. They take time. And I don't know if I'm going to ask, I'm not going to ask you, I can't say I won't ask you, but I will probably only ask you to get it to this point, write the equations, and then, for extra credit, do this. Okay? But not ask you to do this step at all. Find I1, I2, I3 is the final step. And that's, again, it's doable. It just takes time. Any questions, any comments, any thoughts? Well, I wish you the best in your careers. I don't say that I had a good career. I had a career, but it was ups and downs and this and that and whatever. And everybody does have that. So you're not going to escape unscathed totally. But I wish you all to have good careers. Like I said, it wasn't always pleasant. It wasn't always unpleasant. I sure did like what I did, most part. I like being an engineer. And I like teaching other people the same stuff. Conveying that it's not all theory, but it's not. You open a box panel and water flows out or dust flows out or something worse, and you have to fix it, you have to make it work. It's not fun, but you can do that, and that's part of your job. Okay? You're hands-on. I think everybody in here is hands-on person first. Okay, so I'm going to shut this puppy down, and we'll work on that test, and we'll be on to the lab. We'll get the lab done today.